Okay, good morning. Um, Today, again, we will resume our lecture, and then there will be, towards the end of today's lecture, there will be a 30-minute tutorials, and today's Kelvin Wu would give a tutorials on recommender system. So as I have previously mentioned, recommender system is actually a very useful tool in many applications, especially in e-commerce. For example, if you use YouTube, if you're a user of a YouTube, sometimes you'll see recommended videos to you. If you have a Netflix or Disney's users, those video streaming services, the system would also, based on what you have previously watched, recommend certain videos for you too as well, right? And if you are using Amazon, sometimes you'll see a list of recommended items. So all those e-commerce websites, it's been reported that a substantial amount of profit or revenues come from recommender systems. So this is a very important tool. And towards the end of today's lecture, Kelvin Wu will give you a tutorials on some of the basic ideas of recommender system. We could have created a full course on recommender system because there are many different techniques. However, due to the limitations of time, we will not be able to cover a lot. But hopefully this 30-minute tutorial will at least give you some ideas of what the recommender systems is and what's its one or two some of the basic techniques in implementing recommender system. We did not have this section in last year when we taught this course last year. This is a new segment, for this year's offering. But the material that we'll cover in today's tutorial on recommender system will not be in the examination. It's just for your interest only. All right. Okay. So let us resume our discussions. In our last meeting, we talked about association group mining, and just to refresh your memory, just a little recap. So our objective is that given a data set, what we call that looks something like this, which has a collections of what we call transactional records. And each transaction or transactional record here is essentially just a list of the items that the customer has purchased, let's say within a trip to the supermarket. And so if you look at this data set here, it's essentially a binary data set. So we have a number of columns here. Each column represents a certain particular item. Here in this toy example, we have A, B, C, D, E, F, right? And under each column, we have a number of rows. Each one represents a particular transaction or transactional record. And the one here represents the presence of an item in a particular transaction. 0 means its absence, not there. All right. So you're given this kind of like binary data set. And our objective is to derive what we call association rules. And the association rules have the form of X implies Y, where X, Y are set of items, or what we commonly call item sets. The semantics of this association rule is that if a customer purchased the items mentioned in the item set X, then it is very likely that that customer would also purchase the items mentioned in the item set Y. So this is kind of like a prediction, right? We call this association rule. There are some requirements for a rule such as X implies Y to be reported to, let's say, a manager. One of the rules is that there are certain restrictions on the set of on the item set X and Y. They have to be non-empty. They should not overlap, right? So that's one requirement. The second requirement is called a support requirement. We require that the support counts of X union Y to be not smaller than a certain threshold. You can still remember if we express a support as a fractions of n, where n is the total numbers of transactions here, it has to be not smaller than a support threshold, what we call it rho S. And the other requirements is called a confidence requirement. We want the conditional probability, which is expressed by this, to be not smaller than another threshold, rho C, what we call the confidence threshold. Just to refresh your memory, of what we have discussed last time, right? So in our previous meeting, we mentioned the a priori algorithm, which is one of the most well-known algorithms in solving the association reminding problem. And the a priori algorithm essentially consists of two steps. All right. So the first step is to figure out all the frequent item sets. So I look at the data sets that we have, and we try to discover or find out all the item sets that are frequent. And the item set S is said to be a frequent item set if its support count is not smaller than n multiplied by row S. So there is a minimum support requirement, for the items that are mentioned in the rule. This is step number one. And for this example data set that we have here, the set of frequent item sets is listed here. All right. So even with such a small toy example, we have quite a numbers of item sets that we could discover that are frequent. Now, in this example here, we require that the minimum support count of 5 for an item set to be considered as a frequent item set because of the, let's say, 20% support threshold. All right. Now, I also mentioned previously that for this example, we set the support threshold to be 20%, but in practice, you don't have that high a support threshold. Probably you will set it to like 1% or 0.1%. That's more likely in real practice. But just as an example, let's say we set 20% as a support threshold, and then we'll have the minimum support count being 5 for an item set to be counted as frequent. And given that's very small, for example, data set that we have, this is the list of all frequent item set that we can extract from the database. All right. Now imagine that in practice, if you're really running a real supermarket, the data set of the table would be extremely large because we do not have only 1 to A, B, C, D, E, F. We do not have just 6 items. A supermarket could carry, let's say, 1,000 items. So that would be 1,000 columns. And the supermarket would make many more transactions, let's say tens of millions of transactions. So there would be many, many more rows, right? So the numbers of item sets that you could create or that you could derive that are frequent could be a lot more than just this little table shows, right? Just to give you a sense of the scale of the problem. But anyway, the first step of figuring out the association rule is, given the data set, try to figure out all the frequent item sets. And previously, we said that this step number 1, is usually very expensive because if the supermarket carries, let's say, M items, right? Milk, bread, butter, sugar, whatever, right? Then there are essentially 2 to the power M minus 1 non-empty item sets. And that is a huge number if you consider M to be something like 1,000, right? So 2 to the power M minus 1, which is all the possible combinations of the items, is extremely large, right? It's something that cannot be handled. And checking each such item set, whether it is frequent or not, is impractical. It's absolutely infeasible. So we have to resort to what we call the a priori algorithms, which have some way to prune the very large search space in figuring out the frequent item sets, right? So this is something that we discussed about last time. Now, after we have obtained this table, which include 2 things. Number 1, it's the list of frequent item sets. So for example, A, B, BE, BC, CDE, etc. These are all the frequent item sets. And the second thing that we need is the support counts of each of these frequent item sets. That is, all these numbers, all these counts, we also need them, right? Now, the reason why we need all these counts is because we need to check the rules confidence requirement, whether they are satisfied, or whether the rules satisfy the confidence requirement or not. So after the frequent item sets are obtained, such as this table, what we need to do next, which is the second step, all right, is to generate the rules. So how do we generate the rules? Well, we take any frequent item sets that we discover in the first step, and if that item set consists of at least 2 elements, we'll try to generate rules from it or derive rules from it. So what we do is that we take a frequent item set, let's say CDE, and we try to partition it into a left-hand side and a right-hand side. That is, we try to get an X and an X and a Y of a rule, and then check the confidence requirement, whether that satisfy the confidence thresholds or not. So an example that we gave last time was that let's take CDE, which is a frequent item set that we discover here, all right? And there are 6 possible ways to partition the, the frequent item set CD into a left-hand side and right-hand side. Each one of them is what we call a candidate rule. And for each rule, we have to check its confidence, which could be obtained by calculating certain ratio based on the support counts that we discovered in the first step. So in this example here, we figured that these 2 rules, if the confidence threshold is 65%, these 2 rules satisfy the confidence requirements, while the other 4 do not. And so we'll keep the 2 rules that I colored green, and those will be reported. Those are the valid rules. All right. So this is a little recap of how we obtain association rule, right? Now, a while ago, I said that the first step is actually the most expensive. That is, given the data set like this, try to figure out the set of frequent item set and the support count like this. This step is extremely difficult and computationally expensive because of these issues here. And we said that the a priori algorithm is an attempt to try to prune this large search space into a more manageable size so that it is more computationally efficient. And this is the kind of like illustrations of what we call the a priori property. You can still remember. So the a priori property says that if you give me an item set, let's say AB, if this item set is infrequent, that is to say, it doesn't satisfy the minimum support requirement, then none of its supersets is frequent either, right? So if AB is not frequent, it doesn't have enough support, then none of its supersets could be frequent. And therefore, when we are considering the item set, whether they're frequent or not, these shaded ones can be pruned, can be ignored. We do not have to count the support because we are already guaranteed that they cannot be frequent. You understand what I'm saying? All right, so this is what we said previously. So how exactly does the a priori algorithm work? We use an example to illustrate. Yeah. So again, very quickly, just a little recap. So the a priori algorithm goes through certain iterations, right? In the first iterations, we'll prepare a set, what we call C1. This is the set of all size 1 candidate item sets. C1 is very simple. Look at how, what are the items that we have is A, B, C, ... to F, right? So we create 6 counts, 1 for each items in the database, and these are called singleton, all right? And then we go through the whole data set. We scan the database 1 time, all right, to count the support of these item sets, all right? So if you have gone through every single transactions in the database, we scan it once, we'll determine the support counts of the item sets, all right? And in this example here, let's say our support threshold is 5 supports. And then we could for those item sets whose support count meets the support requirement, in this case 5, would be collected into a set L1. This is the set of all frequent 1 item set. All right. So from C1, we scan the database to obtain an L1. All right. And from L1, what we do is that we'll pick any 2 items from L1, join them together to form a size 2 candidate item sets. So in this example here, we have 5 items, 5 size 1 item sets, right? These 5 are collected in L1. So by combining them, we'll be able to get these 10 size 2 candidate item sets, all right? And we call this operations from L1 to C2, right? This is C2, the join operation, right? Because basically we're picking some L1 item set, join them to create a larger candidate item set, right? So we call this a join operations. So after C2 is obtained, again, we scan the database a second time to compute the counts, the support counts of all these item sets. And this is the results. And for those item sets whose support count exceeds or meets our requirement, let's say 5 here, we have AB, BC, BD, and so on. We have like this 7 size 2 candidate item sets that meets the support requirement, and they will be collected into the set L2. All right, so from C2 to L2, we scan the database to obtain the counts and determine L2. Understand what I'm saying? All right. Now, after we have obtained L2, then the next iteration is similar. We pick 2 items from L2, try to join them together to get some size 3 candidate item sets. We put those in C3, scan the database to obtain the counts. Those that are frequent will be collected into the set L3, and so on. And from L3, we'll create C4. With C4, we scan the database to get L4. With L4, we do some joining to get C5, scan the database to check the support count of those items that in C5 to obtain L5, and so on, right? So this is the iterations that we mentioned. Now, one thing that a priori does in what we call pruning is how it applies the a priori property. And this is how the a priori algorithm works. So specifically, if we are going, well, we have obtained this, the set Li minus 1, and if our task is to create or generate the candidate set Ci, the a priori algorithm uses a function called a priori gen to perform this joining operations. All right, let's see. Okay, so specifically what it does is that intuitively, the algorithm needs to pick 2 item sets from Li minus 1, right? Join them together to obtain a size I candidate item set in Ci, right? So how does this join work? Specifically, we will pick an item set X and an item set Y from Li minus 1, right? Remember, Li minus 1 referred to the set of all frequent size I minus 1 item sets. Right? So we pick a pair, X, Y. Now, we would join them if they overlap in I minus 2 of the items that are in there. All right. So on the top right, we have a little illustrations. Okay. So this is, let's say this represents item set X. All right. This represents item set Y. Both of them are taken from Li minus 1. So each one of them has I minus 1 items, right? Now, the way that X and Y are paired up is that if they share most of their items together, except one item from each, okay? So if each one of them contains I minus 1 items, they share I minus 2 items. This is the conditions for us to pair them up, okay? That means that there is one item in X that is not in Y, and there is one item in Y that is not in X. So when we combine them, we get a size I item set. All right. So again, X and Y are size I minus 1. We have one item in X that is not in Y. We have one item in Y that is not in X. We will merge them together. We get a size I item set. Okay. And let me use Z to represent the merge, the results of the merge. Okay. Now, Z is what we consider to be a candidate, something that is potentially frequent. But before we put Z into the set Ci, we do one more checking. Okay, we check if all of its size I minus 1 subsets are all frequent, then Z will be put into Ci. So we pick an X and Y from Li minus 1, join them to obtain a Z. Before Z is put into Ci, we check whether sets has all of its I minus 1 subset being frequent. If so, we can put Z into Ci. Right? So this is the a priori gen algorithm. So here is a couple of examples that we use to illustrate. In our example here, we have BD and CD being in L2. So this is L2. We have BD and CD in L2, right? And we see that there is one item in BD that is not in CD, namely B, right? We have one item, namely C, that is in CD that is not in BD. So we merge them together. That would give us BCD, all right? Now, before we put BCD into C3, we have to check whether all of its subsets are in L2. So there are three size 2 subsets of BCD, namely BC, CD, and BD. All right. And we already know that BD and CD are frequent because they are in L2. So let's check whether BC is in L2 as well. In this example here, we have BC in L2 as well, right? So we have all size 2 subsets of BCD being in L2. So it is safe to put BCD into C3, all right? Now here is another example. We notice that AB and BC are in L2. So we have AB and BC, these two guys are in L2, and we can use them to merge them together to join a larger item set. The result of joining them give us ABC, right? So before we put ABC into C3, we have to check whether all of its size 2 subsets are frequent. We already know that AB and BC are in L2, but what about AC? This is another size 2 subset of ABC, right? So let's check whether AC is in L2 or not. In this example here, AC is not frequent. So we have a subset, namely AC, of ABC that is not frequent. And by the a priori property, we know that ABC cannot be frequent. And so ABC should not be put into C3 for future checking. You understand what I'm saying? All right, so that's basically how a priori works. This is what we call the a priori gent procedure. All right. Okay, so continuing with our example, if this is the L2 that we obtain, we use the a priori gent algorithm to take pairs of item sets from L2, join them together, and consider whether that should be put into C3 or not. So basically from L2 to C3, we do a lot of joining, all right? And eventually, the set C3 that you obtain would contains these 4 item sets. So we have to scan the database again, obtain the support counts of these item sets, and those that are frequent will be collected into the set L3, all right? And so on. And eventually, we get L3 being this. If we take any 2 item sets from L3 and merge them, we'll find that, well, in this case, the only thing that we can generate is BCDE, right? So we have to consider whether BCDE should be put into C4 or not. And so we need to check all of its size 3 subsets to see whether they are all in L3. In this case, we find that BCE, which is a size 3 subset of BCDE, is not in L3, it's not frequent. So that means that BCDE cannot be frequent, and so we do not put BCDE in the set C4. So after this joining, we find that C4 is an empty set, so there is nothing more for us to count, and the a priori algorithm will terminate, right? So hopefully you understand the procedure of the a priori algorithm, all right? So in this example, now this is the a priori algorithm's pseudocode. Again, you do not need to remember these details, all right? Just the concept. Oh, by the way, in the final exam, you have already taken the midterm exam, right? So in the midterm exam, we provide you with some toy data set, and we ask you to carry out certain determination. For example, in the midterm, the constructions of like a decision tree or something like that, right? So those are the procedure that we mentioned in class. For example, how to build a decision tree. Here we talk about how do we find frequent item sets. Maybe in the next chapter, we'll talk about how we could perform cluster analysis, how to carry out those procedures. So the final exam would be quite similar to what you see in what you saw in the midterm, which is some of these questions we give you some toy data sets, right? And then we ask you to carry out some procedure, for example, like building a decision tree, or finding some certain frequent item set, or doing some cluster analysis, right? So basically, the midterm serve the purpose of giving you a preview of like what the final exam will be like. Okay, although in the midterm we didn't cover association analysis, we haven't finished it yet, but you get the ideas of some of the questions. Of course, there would also be some questions that ask you more of the conceptual levels things. For example, what is overfitting, things like that. So some of those questions would kind of like short questions, which ask you to test whether you have enough understanding of certain basic concepts and principles. Okay. All right. But we would not ask you to recite these details, of the pseudocode. We'll never do that. Okay. All right. Now, if you think about the a priori algorithm that we just mentioned, although it is a practical solution because it does a lot of pruning of the item set, so it doesn't count to the power n-1 that many item sets support counts. However, in practice, the a priori algorithm is still quite expensive procedure. So here, as I said, although a priori gives a feasible solutions to the association reminding problem, it is still very demanding, both in terms of CPU time and also I/O cost. All right. Now, the reason why the a priori algorithm is very CPU intensive, you have to do a lot of computations, that comes mostly from support counting. Right. So you remember that in the procedure here, what you need is that you prepare in each iterations, we will have a candidate set, right? And then we have to scan the database. And for each transactions in the database, we have to check whether the transactions contain or support any one of these item sets, right? And that requires a lot of subset testing. So essentially, we have to test whether, let's say, BCD is a subset of the first transaction. If so, we have to increment the count, right? We have to check whether BCE is a subset of the first transactions. If so, we have to increment the count, things like that. So intuitively, we have to do a lot of subset testing, okay? And that requires a lot of CPU time. And that's why it is CPU intensive, okay? And also, the a priori algorithm is also very high in terms of I/O cost. The reason is that we have to scan the database many times, right? Basically, we have to scan the database once for each iterations of the a priori algorithm, right? Because we have to scan the database to obtain the support. Now, previously, I said that this is the kind of like the structure of the a priori algorithm. So what do I mean? Well, we start with this candidate set C1. So this is the set of all size 1 candidates, basically derived from the items that are there in the data sets, right? And from C1, what do we do? We scan the database to count the support counts of the item set in C1 to obtain L1, to check which one of them are actually frequent. So from C1 to L1, we have to do a lot of scan. We have to do one scan of the whole database and to do a lot of support subset testing, right? So this is what we need to do from C1 to L1, okay? Now, if L1 is obtained, what the a priori algorithm would do is that it would apply the a priori GEN procedure, join the item sets in L1 to obtain a C2, right? This is a set of all size 2 candidate item sets. And from C2, we would scan the database again, doing some support counting to obtain L2. L2 is a set of all frequent size 2 item sets, and so on, right? So again, one more time, from a C1 to L1, from C2 to L2, from C3 to L3, or in general, from CI to LI, we have to do one scan of the database, okay? And from L1 to C2, L2 to C3, or LI to CI+1, this is about the a priori GEN procedure, joining the items to obtain a candidate item set, okay? Now, so the question here is, suppose I have K being the size of the largest frequent item sets in the data set. Right? So let's say K is the size of the largest item sets or largest frequent item set in the data sets. How many passes, how many times do we have to scan the database? So if the largest frequent item set contains K items, then how many times do we have to scan the database? Well, the answer is K or K+1 times, right? Why? Well, first of all, we notice that from a CI to obtain an LI, that takes one database scan, right? So from C1 to L1, that's one database scan. From C2 to L2, there's another database scan, and so on, right? So if we get from CI to LI, that is I database scans. So if K is the size of the largest frequent item set, well, what do we see is that we must have a CK, and then we scan the database again, the Kth time, to obtain LK. And if K is the size of the largest frequent item set, that means that LK is non-empty, right? And then from LK, we do a priori gen to obtain CK plus 1. And we might need to scan the database one more time to obtain LK plus 1, right? But if K is the largest frequent item set that we have, that means that LK plus 1 must be the empty set, right? So how many times do we have to scan the database? Now, up to this point, we have to scan the database K times, right? Because from C1 to L1, one time, C2 to L2, two times, CK to LK, that's the Kth time that we have to scan the database, right? So whether we need to do this scan or not, from CK plus 1 to LK plus 1, whether we have to do this additional scans or not, depends on whether CK plus 1 is empty or not, right? So if CK plus 1 is empty, then there's nothing for us to scan in the K plus first iteration. So the total numbers of scan would be just K, right? However, CK plus 1 could be non-empty. And in that case, we still have to carry out one more scan to get to know that none of them is actually frequent. So in this case, we have to scan the database K plus 1 time, right? So if K is the size of the largest frequent item sets in the data set, we will have to scan the database either K or K plus 1 time, right? Okay, but in any case, that's quite a number of scans, of scanning of the database. So that requires a lot of I/O. And that's why the a priori algorithm could be quite expensive in terms of I/O as well, right? So what people or what researchers have done is that they have been trying hard to propose different approaches to speed up a priori. I'm sure there could be something like 1,000 research papers that talks about how a priori algorithms could be improved in terms of efficiencies. Of course, we do not have enough time to cover all of those techniques because there are so many of them. Here, let me just very briefly mention a few, just to give you an idea of how the a priori algorithm could be improved, all right? So some of the techniques include transaction reduction, sampling, hashing methods, and distributed algorithms. Because of the limitations of time, I probably would just cover the first three, mention them very briefly, all right? Oh, by the way, in today's discussions, we will get into some of the details of some of the algorithms. Some of those algorithms details are a little bit more complex. And so I'll try my best to explain. If you do not completely understand, let me know. I would be glad to repeat, right? Okay, so the first approach for one of the approaches for improving the efficiencies of the a priori algorithms, it's transaction reduction. The idea is very simple. We observe that if a transaction does not contribute any support to any candidate item sets in a certain iteration, let's say the ith iteration, then it will not contribute any support counts in the next or the I plus first iterations either. So these transactions could be safely discarded after the ith iteration. So what do I mean? Let me further illustrate. Now, let us consider an item set, let me call it X2 in CI plus 1. So this is a candidate, X2 is a candidate item set in the I plus first iteration. So we generated it. We want to see what is the support count, all right? So to obtain the support count of X2, we have to scan the database to check which transactions support X2, or in other words, which transactions contain X2, right? So that's what we needed to do. Now, notice that X2 is in CI plus 1, right? And the fact that X2 is generated means what? It means that it must come from the merging of some item set in Li, right? So that means that there must be, it must be that all size I subset of X2 are frequent, right? In order for X2 to be put into Ci, the a priori Gen algorithm have to ensure that all size I subset of X2 must be frequent in order for it to be qualified to be put into Ci plus 1, right? And so all the subset of X2 must be frequent, must come from Li, all right? But what is Li? Well, any item set in Li comes from Ci, right? Because Li is just a subset of Ci. In particular, those item sets in Ci whose support counts are large enough would be put into Li. So any item set in Li must be in Ci as well. That is to say, consider any item set X2 in Ci plus 1, we must be able to find an item set X1 in Ci such that X1 is a subset of X2, right? This is the logic, okay? So now, if we consider any transaction T in the database, all right? And let's say this transaction T does not support X1. That means that X1 is not a subset of T, all right? But given that X1 is a subset of X2, and if X1 is not a subset of T, it means that X2 cannot be a subset of T either, right? So that means if a transaction in a database, if it does not contribute to any support count of anything in Ci, then T cannot support any item set in Ci plus 1 either. So we will not contribute any support count to the candidate item set in Ci plus 1 either. And so if a transaction T, during the scan of the database, we find that T doesn't support any item set in Ci, that transactions could be safely discarded. In the next iteration, we don't have to worry about it because this is not going to contribute any support to any item set in Ci plus 1 either, all right? And this is what we call transaction reduction, okay? So as we move along, as we go from C1 to L1, L1 to C2, C2 to L2, etc., we can progressively remove some of the transactions from the database from consideration. We do not have to perform any subset testing that involve those transactions, all right? Because they would not be able to contribute in the next iterations. So that would save us some computational and scanning cost. So this is a very simple strategy, all right? Okay, any question? No? Now, the next one is slightly more mind-boggling. So again, I will try to explain. But again, if you don't understand, please let me know, okay? So the next approach, which is a very natural approach, is to do sampling. If the high cost of a priori come from subset testing and also database scan, like say CPU and I/O, what do we need to do to make it faster? Well, just to make the database smaller, right? With fewer rows, then you do not have to spend so much I/O. With fewer transactions, you will have to do less amount of subset testing, right? So the ideas of speeding up a priori would be instead of using your whole complete data sets, we take a sample, okay, and just mine the sample data set, okay? And hopefully the sample will be smaller. And so this is the illustrations. We have a data set D. We would obtain a sample, let's say D hats, all right, which is just a random sample from the original data set. So D hat, the sample would be smaller, and therefore the a priori algorithm could execute faster with the smaller sample compared with the whole data set, right? So based on the sampling approach, we have two options. Option one is instead of scanning the whole data set, only a fraction or a sample of the data set is used. So we perform a priori algorithms on the sample only. All right. So this is the first option. This is very straightforward. Now, the second option is to do a little bit more. So here, again, from the original data set D, we obtain a sample, and then we apply the a priori algorithm onto the smaller sample to obtain some results. However, for the second option, we'll do a little bit more just to verify whether the sample is good enough, whether the mining result or the frequent items that you obtain from it are a good representations of the original data sets. Right now, so here, now things get a little bit more complicated again. Let me know if you want me to repeat, all right? Okay, so what do we do? Well, when we apply a priori to the sample, we will obtain, as we have previously mentioned, going through the sequence of steps, right? That means that in the process, we will have created a number of candidate item sets, namely C1, C2, C3, ... CI, and so on. We will also obtain some frequent item sets of various sizes, let's say L1, L2, L3, ... and so on, right? So we will create all these CI and LIs during the process, all right? So when we apply the a priori algorithm onto the sample, we obtained two sets. One we call C, and the other one is called L. So basically, C is the union of all those CIs. So C1, C2, C3, we reunion all of them. That would give us the set of all candidates item sets that we have ever generated. You understand what I'm saying? All right, it's just the unions of all those Cs, okay? L, it's similar. L is a set of all frequent item sets, regardless of their sizes. All right, so we merge L1, L2, L3, ... together, and that create the whole set L. So this is the set L is the set of all frequent item sets that we discover from the sample. Okay, so when we apply the a priori algorithm onto the sample, I get a C and I got an L. All right, these C and L are with respect to the sample, to the smaller sample, not with respect to the whole original data set, because we apply a priori only to the sample. Okay, now what do we do is that we find this set, which is C minus L, and this is called the negative border of the mining results. All right, so so C is the unit of all the CI, L is the unit of the LI. So what is so interesting about the negative border? Well, if you think about it, an item set X is in the negative border, which is C minus L, if X is infrequent and all of its subsets are frequent. So these are the characteristics of the item sets in the negative border. All right, why? Well, first, if an item set X is inside the set, it means that it must be in C, right? So what would be an item set X that you would put into some candidate sets? Well, first of all, let's say if X has L item, it's an L item set, so that it has L items. If X is put into C, it means that all of its L minus 1 subset must be frequent, right? So X in C means all L minus 1 subsets of X are frequent, right? So this is one property. And the other thing is that because X is in C minus L, so that means that X is not in L. So that means that X is not frequent itself, right? And therefore, if X is in the negative border, C minus L, it means that X itself is infrequent. It's not frequent because it is not in L. But because this is in C, it means that all of its size I minus 1 subsets are frequent, okay? So this is the properties of the item set in the negative border. So how do we use this negative border to verify whether the mining result with respect to the sample is a good representation of the original data set? Is that what we could do is that we verify that all such X in the negative border with respect to the sample also carry these two properties. with respect to the original data set D. All right. So verify all subset X in the negative border with the whole data set. That is, check whether X is infrequent with respect to the original data set D, and that all X subsets are frequent with respect to the data set D. And if so, the research found that then the mining result that you obtain from the sample is a fairly good approximation of the mining result of the original ones. All right. So again, one more time, the idea is from a data set D, we obtain a sample, smaller one. We apply a priori onto this sample to get the mining result. The mining result includes all the CIs, includes all the LIs. With this CI and LIs, I get C and L, right? I find the set C minus L. This is called the negative border. And then for each transaction, for each item set X in the negative border, the fact that it is in the negative border with respect to the sample means that X is infrequent, all right? And that all of its subsets are frequent. So these are the two properties that must be true for X with respect to the sample, okay? So to verify whether this mining result is good, we also want to verify these two properties to see whether these two properties for X is true, not with respect to the sample, but with respect to D, all right? So how do you check it? It's very easy, because what you need to do is that you take X, right? You scan the database D to see, to check its support counts, all right? If it has enough support count in D, then you say that, well, X is frequent with respect to D. Checking whether it's so you can check whether X is infrequent or not with respect to D. And then checking whether its size, let's say L minus one subsets are frequent or not, it's just the same thing, right? So you scan the database, you'll be able to get to know whether X should be an item set in a negative border with respect to the original data set D, right? So if you take the mining results from the sample, consider all the negative border item sets with respect to the sample, verify them that they are also should be in the negative border in respect to the whole data set, then researchers found that the mining results that you obtain from the sample, it's a fairly good approximations of the original data set. All right, so you get, so the application of the a priori algorithm is based on a smaller samples only, so it's faster, all right? And then, but you have to do one more step, which is to verify, all right? And if the sample is a good enough sample, then the verification would pass. Okay, so that's the, that is one idea. Now, another approach to speed up a priori is the hashing approach. So the idea here is this. Now, the amount of time that we spend on support counting depends on the size of the candidate set. What do I mean? Well, let's take a look of any iterations in the a priori algorithm. Let's say this one. This is the second iterations, right? So what we have is this set C2, all right? And we need to count the supports of all these candidate item sets. So what do? Well, a priori will scan the database and do a lot of subset testing, right? So it consider, for example, the first transactions and ask, well, which item set in C2 are supported by the first transaction? So it has to perform a subset testing to see whether AB is a subset of transaction one. You have to test whether AC is a subset of transaction one and so on, right? So obviously, this step is expensive if the candidate set is large, right? The more item set that we have in the candidate sets, the more counts we need to consider, and therefore more subset testing will have to be done, right? Okay, so here is a table that shows you in practice which iterations would have a very large candidate sets, right? So here is an experiment that we did. We take some supermarket data sets, right? And the first row here illustrate I, which is the item set size. And the second row here refers to the size of the candidate sets. So how many candidate item sets do we need to count across the different iterations of the algorithm, right? Now, in this example here, the supermarket carries 1,000 different items, and therefore there are 1,000 different counts in C1, one for each item. Okay, and if you look at this table, you see that the second iteration is very large. I mean, in terms of the numbers of candidate items that we have, it's more than 200,000 in this particular example that we did as an experiment with some specific supermarket data set. All right, compared to the other iterations, for example, in this third iteration, we have about 1,000 candidate items set to be counted. In the fourth iteration, it's also about 1,000, and then the numbers kind of like they become smaller and smaller. But if you look at all these numbers here, you notice that the second iterations is very expensive because there's so many item sets in the candidate sets that we need to do the counting and support testing, right? And in practice, what we found was that we look at different cases across different applications, and we find that at least from those example applications that we try, typically C2 and sometimes C3 are very large compared to the candidate set size in the other iterations. All right. So iteration 2 should be the target of optimizations. If we want to make things fast, we need to look at the pain point, right? So this is the most expensive iteration. So let's do something about it. Let's try to make it faster. Okay. So the hashing approach is a method that tries to specifically make the second iterations of the a priori faster, because the observations is in general, the second iterations involve usually the largest numbers of candidate item sets. So this is how the hashing approach works. So we create a hash table, let me call it B, with a certain numbers of buckets, let's say R. All right, so these buckets are B0, B1, ... to BR minus 1. Each one of these buckets is a count. Okay. Now, during the first iteration of the a priori algorithm, we have to scan the database to obtain L1 from C1. We have to count the support count of all the size 1 candidate item set, right? So we do a little bit more in the first iteration. Hopefully, that would help us save a lot of effort in the second iteration. So in the first iteration, what are the additional things that we do? Well, besides counting the support of the candidate in C1, well, the hashing approach would do the following additional steps. For each transaction D in the dataset D, we will enumerate all item pairs from the transaction. So for example, if the transactions contains 3 items, let's say U, V, and W, let's say milk, bread, and butter, right? Then what this algorithm would do is that it would enumerate all pairs, all right? Okay, from the transactions. Well, if that transaction contains 5 items, then that would be 5 choose 2 numbers of pairs, so on. And then for each such pair, we will increment the count of this bucket, where H here is a hash function. So HXY is the hash values of the pair XY. We compute a little hash values of a pair, and then we increment the count of the corresponding buckets. All right. So this is the additional step that we will do in the first iterations. Okay. So after the first database scan, we'll have determined L1, and we need to generate C2 using the a priori gen procedure. However, our objective here is to make this C2 much smaller. So before we count the support of all these thousands or hundreds of thousands of item sets, we try to make this set smaller. We try to see whether some of these item sets in C2 can be thrown away. All right. And with this hashing approach, the idea is that a candidate to item set XY in C2, that is, or an item set XY in this, we try to see whether we kick it away. Well, this item set will be removed from C2 if this bucket value is less than the support requirement. All right. The rationale is that, let's say you have 3 pairs, let's say A, B, C, D, and E, F. Let's say all of them has the same hash values. something like L. Then when you encounter the occurrences of an A, B in the transactions, you would increment this bucket count, right? So essentially, the bucket Li, this count is the sum of the support count of all of these pairs, right? And therefore, for example, the support count of AB must not be larger than this bucket count, right? So what do we do is that we check whether this bucket count is less than the support requirement. And if so, we know that all of these support counts has to be not reaching the support requirement. So they can be removed, all right? So again, given an XY in C2, before we start counting in the second iteration, we try to see whether we can remove it by checking whether this bucket count is less than the support requirement. If so, XY can be safely removed with doing accounting. So hopefully, the second we can, before we count the support of these hundreds of thousands of item sets, we can significantly reduce this number, and so that the second iteration will be less costly. And in practice, people found that this approach is very effective. Okay, so this is another method for speeding up a priori. Okay, so there are many others. As I said, there are many others approaches to speed up a priori. One approach would be to do distributed algorithm, that is to say, use multiple machines to do the counting. But how do we coordinate these machines so that the counting would be very effective? Would be, it's some, there are a lot of studies about it. Unfortunately, due to the limitations of time, I'm afraid that I have to skip this part. Right. So one last thing for you to study for the exam. I will skip this a few slides, which talks about the distributed algorithms in mining the frequent item sets. Okay, now another thing that we would like to discuss, it's about some compact representations of the mining result. So previously, many slides back, we said that given the data set, let's say this one. All right, our objective is to first find out all the frequent item set. That is, we want to compile this table. This table consists of all the frequent item sets as well as their support counts. So this is something that we need. And this is the result of the first step of generating the rules. The second step being deriving the rules and check the confidence, right? So the first step is to try to find out all the frequent item sets as well as the support counts. We said that, well, this part is typically very expensive. And in fact, this list, this set of all frequent item sets typically is very large, all right? Even though with the Veritor example, we see a small table, but in practice, this could be very large. So we want to see whether there is a more compact way of representing the set of all frequent item sets. All right. So again, the result of the first steps of association rule mining is to find all the frequent item sets, but this sets could be huge, and we want to have a more compact representations of the set L, the set of all frequent item set, and also the support counts. All right. Now it turns out that we do not need to remember all of the frequent item sets and the support counts. We can compress this mining results quite effectively. In order to understand that, we have to understand two concepts. One is called maximal frequent item set, and the other is called closed item set. All right, so let's take a look at what they are. Right? Now, an item set is called a maximal, is said to be maximal frequent if it satisfies two conditions. One is that it itself is frequent. That is to say, it satisfies the support requirement. The other conditions is that none of its immediate supersets is frequent. That is to say, if you give me an item set X, if X is maximal frequent, two conditions. Number one, X is itself frequent. In order for it to be maximal frequent, so it has to be frequent. The other condition is that it is maximal. What does it mean? It means that if you add any items to X, you make it infrequent. That's why we call it maximal. Okay. So again, X is maximal frequent if it is frequent. And if we add anything to it, that is any superset of it, it's infrequent. Then we call X to be a maximal frequent item set. So here, let me use an example to illustrate. Here we have 5 items in this example, namely A, B, C, D, E. All right. Altogether, there are 31 non-empty item sets, which are being arranged in this lattice. Okay. And so in this illustrations here, the item sets that are shaded, let's say A, B, C, D, or A, B, C, these shaded nodes, the shaded item set are not frequent. Okay. And all the other are frequent. Okay. Including, for example, CD, including, for example, ACE. All right. Now we can draw what we call a border that separates the frequent item sets from the infrequent item sets. All right. Now, if you count the total numbers of frequent item sets, include A, B, C, D, E, AC, AD, AE, BC, and so on. So if you count, there are in total 20 frequent item sets in this example. All right. Now, in order to identify which item sets are frequent, it turns out that we do not need to remember all these 20 frequent item sets. All we need to know is what are the maximal frequent item sets. And in this example here, there are only 3 maximal frequent item sets, and they are colored this kind of light bluish notes. All right. So AD, ACE, and BCDE are the only maximal frequent item sets in this example. All right. So, for example, like, what about AD? Is it maximal frequent? Well, first of all, it is frequent, and any superset of it. Well, because we have 5 items, so the immediate superset of AD would be ABD, right? ACD, and also ADE. You notice that all of its immediate supersets, they are all shaded, they are not frequent, right? And so AD is maximal. So if you add anything to it, you make it infrequent, and that's why we call it maximal frequent, right? So AD is a maximal frequent item set, so is ACE, so is BCDE. And let's do another example. What about BD? Well, let's check its immediate superset. We have ABC, we have BCD, and we have BDE, right? Now you notice that BCD, this is a superset of BD, it is also frequent, and therefore BD is not maximal frequent, because you can still add a C into it, and it's still a frequent item set, right? So BD is not maximal frequent. So if you check all these frequent item set, you'll find that AD, ACE, and BCD, these 3 are the only maximal frequent items. Now, we can, well, this is fairly easy to prove that an item set X is frequent if and only if it is a subset of a maximal frequent item set Z, where Z is maximal frequent. Right? This is fairly easy to prove this. Okay? An item set X is frequent if and only if it is a subset of some maximal frequent item set. All right. I'll leave it as an exercise, for you to figure this out to prove this. Okay. So in other words, if you are given the maximal frequent item set, let's say AD, AC, and BCD here, to enumerate all the frequent item set in the data set, all you need to do is to enumerate all the subsets of the maximal frequent item set, and that's the whole set of the whole collections of frequent item sets. All right. Okay. So that's one thing. So first, again, we have 20 frequent item sets in this example, but we do not need to remember all of them. only 3 would be sufficient. All right, the maximal frequent item set. All right. However, knowing the maximal frequent item sets only allow us to determine which item set is frequent and which item set is infrequent. But that does not tell us the support count of the frequent item sets. All right. That means that if our objective is to compile this table of all frequent item set and the support counts, if we know what the maximal frequent item sets are, that tells us these information without the counts. Okay, that's not sufficient for us to generate a rule. We also need these counts as well. So knowing the identities of the frequent item set is not sufficient. Right? So what's next? Well, what we need to do or to record in order to obtain the support count of the frequent item sets is what we call the closed frequent item set. All right. So let me explain what do we mean by closed item set. Okay. Now, an item set X is a closed item set if none of its immediate supersets has the same support as X. All right. So here, let me use some example to illustrate. Let's consider the item set AB. All right. Now, in this example, we have 5 transactions. We have 4 items. So this data set is different from the one that I used to illustrate this one. Right? Okay. So in this data set, we have 5 transactions. Let's say we have 4 different items. Let's say A, B, C, D. All right. Let us consider the item set AB. Its support count is 4 because out of these 5 transactions, 4 of them contains AB. Right. Now, let's see whether AB is closed or not. So let's check its immediate superset. We have 4 items, A, B, C, D. So there are 2 immediate supersets of AB, namely ABC and also ABD, right? These are the 2 immediate supersets of AB. See, do they have the same support count as that of AB? No. That means that AB is closed. None of its immediate supersets has the same support as itself. And so AB is a closed item set. You understand what I'm saying? All right. Let's take a look at another example. Let's say BC. All right. BC is here. Its support count is 3. What are the immediate superset of BC? They are ABC and also BCD, right? Now we see that BCD has the same support count as BC. Therefore, we found an immediate superset of BC that has the same support count as itself, and therefore BC is not closed, right? BC not closed. Do you understand what I'm saying? All right, so that's the definitions of closed item set. If you give me X, if you ask me is this closed, I check all its immediate superset. If none of them has exactly the same support count as X, then X is closed. It's slightly complex, right? Okay. Now, so what do we need? It's this is quite interesting. Now, let's say here we have another data sets. Again, 5 transactions, but this time, let's say we have 5 different items, A, B, C, D to E. And this, on the right-hand side here, you see the lattice that shows all possible item sets. All right. Now, in this illustrations, I labeled each node with some red numbers. Those red numbers indicate which transactions in the database support the item set. For example, if you look at the item set A, it is labeled 1, 2, 4. It means that transaction 1, transaction 2, and transaction 4 contains A. All right. So the numbers of red numerals in the label refer to the support count of the transaction. So support count of the item set. So the item set A has a support count of 3 because transaction 1, 2, 4 supports it. So its support count is 3, and so on. All right. Now, in this example here, let us assume that we have a minimum support of 2. All right. So an item set has to have a support count of at least 2 in order to be considered frequent. Let's say that's the case. All right. Then what we could show is that in these illustrations, we want to identify some maximal frequent item sets and those closed frequent item sets. Right. First, the nodes that are shaded, these are closed frequent item sets. All right. And those nodes that has a blue kind of like enclosure, those are the maximal frequent item sets. Right. So in this pictures here, you check that there are altogether 9 item sets that are closed, frequent, and there are 4 maximal frequent item sets. Now, one thing that you notice is that any maximal frequent item set must also be closed frequent. Right? That could be also easily proved, and I will leave that as an exercise. So what do we need in order to represent the whole table of frequent item set and the support counts? Interestingly, is the following. First, we need to know which item sets are maximal frequent. In this example, I need to know that CE, DE, ABC, and ACD are maximal frequent. All right. The second thing that we need to know is the support counts of all the closed frequent item sets. That is, I need to know the support count of all the shaded nodes. Yeah. So the total number of things that I need to know in this example is just 9. All right. I only need to know the support counts of 9 closed frequent item sets, and I claim that I can deduce the support counts of all the frequent item sets in the database. All right, so here let me show you how. Okay, well, first of all, so if you are given an item set, let's say X, all right, and I want to know whether I want to care about it or not. Well, first of all, I need to determine whether it is frequent, and if it is frequent, what is the support count? Okay, in order to generate the table that was shown previously. So how do you determine whether X is frequent or not? Well, if I know which are the item set that are maximal frequent, to determine whether X is frequent or not is easy. We simply check whether X is a subset of any frequent or of any maximal frequent item set. If so, X is frequent, right? Now, suppose X is frequent, then the next thing that I need to know is what is the support count? What is the support count of X? All right, this is the second thing that I need to know. Okay, now there are 2 cases. Case 1, X is closed. All right, X is a closed frequent item set. Do we know its support counts? Yes, because we said that we recorded all the support counts of all the closed frequent item sets. So if X is a closed frequent item set, we have recorded its support count, so we know, right? So the only thing that we need to handle is that X is not closed. So X is frequent, but X is not closed. All right. So if X is frequent but X is not closed, then how are we going to determine support counts? So here, instead of going through an algorithm and showing you how that is done, let me use an example to illustrate. All right. In this example here, we notice that now, although I'm showing this whole picture, but let's say we have only recorded the informations of the shaded nodes. Those are the things that we have registered, we have recorded. The other, we do not know, right? Now, let's take a look of the item set A. So suppose I want to know if A is frequent or not. That's easy. We check whether A is a subset of any of these maximal frequent item set. It is, because A is a subset of ABC. So A must be frequent, right? And next, we want to know what is the support count of A. Well, the support count of A is not recorded, so we do not know, but we can deduce it, all right? Now, the fact that A is not closed by, by the definitions, we know that there must be there must be an immediate superset of A whose support count is equal to the support count of A, right? So that means that the support, let's see. Oops. Give me a second. Some minor technical problem. I'm encountering some minor technical problem here. Why don't we take a 5-minute break while I fix the problem? Okay, sorry about it. Okay, now, first of all, if you are given an item set X, suppose I know that this item set X is not closed. All right. Now, what does it mean? It means that if I consider all the immediate superset of X, let's say the immediate superset of X are Y1, Y2 to something like YK, all right? So let's say these are the immediate superset of X. So X is a subset of them, all right? Now, let's say the support count of X is P, is some number P. And well, the fact that X is a subset of Y1, Y2 to YK, by the a priori property, we know that the support count of Y1, Y2 to YK, etc., the support counts cannot exceed P, right? They all have to be less than equal to P, right? Because Y are the superset of X, and the support counts cannot be more than the support count of X. That's by the a priori property, right? Now, if X is not closed, by definition, it means that there must be at least one of the immediate superset of X that has exactly the same support count as X. All right? So that means that the support count of one of those Y's must be exactly P. Okay? So without loss of generality, let me say that Y1 support count is P. So now what we know is that Y1 has a support count of P. For the other Y's, the support count cannot be more than P. So it means the maximum of all the support of these immediate supersets has to be equal to P, right? So that means that the support count of X, which is P, can be determined by the maximum of all the support of the Y's, right? So now let us go back to our previous discussion. I want to know the support count of A. What is it? I notice that A is not closed, so its support count has not been recorded. And we can determine the support count of A by this observation. That is to say, the support count of A must be equal to the maximum of the support counts of the immediate supersets of A. So what are the immediate superset of A? Well, we have AB, AC, AD, and AE. These are the immediate supersets of A, right? So what is the maximum support count of AB, AC, AD, and AE? All right. Now, AB, do we know its support counts? The answer is no, because it is not shaded. This is not a closed frequent item set, so its support count is not recorded, all right, in our data set. But we know that AB is a frequent item set because it is a subset of ABC, all right, but we do not know its support counts. Okay. However, and therefore, the the support count of AB would have to be determined. We can do this recursively. So the support count of AB has to be the maximum of the support count of AB's immediate supersets. So what are the immediate supersets of AB? They are ABC, ABD, and also ABE, right? And first of all, we notice that ABD is not frequent because ABD is not a subset of any maximal frequent item set. That means that ABD's support counts, that is ABC, ABD, and also ABE, right? Since ABD is not frequent, because ABD is not a subset of any maximal frequent item set, therefore its support count must be strictly less than 2, because 2 is the minimum support requirement that we have in this example. Likewise, ABE is not frequent because this is not a subset. Okay. All right, so the support count of AB has to be less than 2 as well. What about ABC? Well, ABC is a closed frequent item set, so its support count has been recorded. And its support count is 2 because it is supported by transaction 1 and 2. So this support count is equal to 2. And so we can deduce that the maximum has to be 2, right? And therefore, the support count of AB has to be equal to 2. And likewise, for AC, well, this is a closed frequent item set. So its support count has been recorded, and its value is 3 because it's supported by 3 transactions, namely 1, 2, 4. So we know that the support count is equal to 3, right? By similar approach, you can deduce that the support count of AD is 2, and you can also deduce that the support count of AE to be less than 2 because this is not frequent. All right, and so the maximum of all these would be equal to 3, and therefore we can deduce the support count of A, which is 3, which is correct because transaction 1, 2, 4 supports it. All right, so from this example, we illustrated that all we need to do is to record the identities of the maximal frequent item set and also the support count of all the closed frequent item sets. And we can use these informations to deduce the support count of all frequent item sets, right? And so that would be a more compact representation. So we do not need to record the support counts of every single frequent item set in the data that can be derived from the data sets. So this picture illustrates the relationship between some of the concepts that we have just mentioned. We talk about frequent item set, closed frequent item set, and also maximum frequent item sets. And these are the relations. In fact, all maximal frequent item sets have to be closed frequent item sets, and all closed frequent item sets are frequent item sets themselves as well. All right. And as I just discussed, we only need to know the maximum frequent item sets and also the closed frequent item sets and the support count in order to figure out all the frequent item set and the support counts. And with those, we can determine all the association groups. All right. And finally, for this chapter, the final things we want to mention is high utility item sets. Okay. So previously, when we said that when we consider an association rule, let's say X implies Y, we have a support requirement. In particular, we require that the support count of X union Y has to be not smaller than the number rho X multiplied by N, where N is the total number of transactions in the data set. Now, if you can still recall, this requirement, the support requirements, is there to make sure that the rules is significant, right? So what do we mean by this rule being significant? Well, we require that the items mentioned in the rule, that is the support of X unit and Y, the numbers of transactions in the data sets that concern these items mentioned in the rule are many. All right. That is to say, the items mentioned in the rule are being sold quite frequently. And so the rules X implies Y matters. It's significant because these items represent a significant contribution to the revenues of the company, of the supermarket, right? So this is why we have the support requirement. But it turns out that support count is not the only way for measuring the significance of a rule. For example, some people would like to use what we call the utility measure to evaluate the importance of the items that are mentioned in the rule. So here's the data model. Now, each transactions T in the data set reports the items and the quantity sold. That is to say, previously, when we talk about association rule mining, we only care about the presence or absence of an items in the transactions. However, in practice, we also know about the quantities of the items being bought as well. So the utility here, we take into account the quantities of the items being sold. All right. Let me use QAT to represent the numbers of units of item A that is sold in a transaction T. All right. And for each item A, I also want to learn about its profits, or the amount of profit that we can make by selling each unit of an item A, right? And we use PA to represent the unit profits of the item, right? And the problem definitions of high utility item sets as opposed to frequent item sets is that given a transaction T and an item set X, if the transaction T support X, that is to say all the items mentioned in X are present in the transaction, then the profit of this item set X by the transaction T is given by this formula. All right, we use sigma XT to represent the profits, which is quite easily understood. This is like for each item in the transaction X, for each item A in the transaction X, we check how many units of it is being sold in the transactions, multiply that by the unit profits. So essentially, this term gives us the amount of profits that we make by selling the those items A in the transactions, right? And then we consider all of the items in this item set X, sum them all up, and that is the total profits, right? This is the total profits that are contributed by the items in the item set X within the transaction T. Okay, so the utilities of an item set X in the whole data set D would be the sum of all of these individual contributions by the transactions. All right, so this is the total profits that we can make by selling the items in the item set X across all the transactions in the data sets. All right, and we use pi XD to represent this value, and we call this the utility of the item set X. So the ideas of high utility item set or high utility rule, association rule, is essentially the same problem as association rule that we have mentioned, except that previously in our association rule analysis, we use support count as the requirement of whether a rule is valid or not. A rule has to attain enough support count in order for it to be reported. But with high utility model, we measure the importance of a rule, not in terms of the support count, but by the utility of the item sets. All right. So the objective here is to find all items at X such that its utility, instead of support count, exceed a threshold. And we use a mean U here to denote the utility, the minimum utility threshold. All right. So essentially, by counting utility instead of support count, we are here a little bit more towards the amount of profit that is being made. All right. So even an items that are not being sold very frequently among the transactions in the data set, as long as its profit is high, then we still want to know about them. So that's the idea. All right. Okay. So here's an example of how do we find the utility. Let us consider the item set X being AE, and let's say we have this data set D. All right. So among these 5 transactions, we notice that transaction 1 and transaction 3, these 2 transactions contains or support AE, right? So transaction 1 here we have A and we have E. Transaction 3 we also have A and E respectively. The other transactions do not support this item set AE. All right. So what is the utility of the item set AE across all the transactions in the data set? Well, let's check. Transaction 1 sell 5 units of A and 3 units of E. And let's say this is the profit table. So for each unit of A sold, we make 3 units of profits. So for the first transaction, we sell 5 units of A, and therefore the amount of profit that we gain would be 5 multiplied by 3. And the first transaction sells 3 units of E, and the unit profit is 5 for each E. So this is the amount of profit that we made by selling those E in the first transaction. So this is the amount of profit that we made by X in the first transactions. Likewise, this is the amount of profit that we made by selling the items in X in the third transactions. So the sum of these, this is the total utility, of the items at AE. All right. So again, the ideas of using high utility or high utility association rule is to find those rules whose items mentioned in the rule has attained an enough amount of utilities instead of using support counts to measure the rule's importance. All right. So that's about it for chapter 5. Do you have any questions? If not, then we will proceed to chapter 6. Okay. Now for chapter 6, first of all, we have some reading assignment. Please go through pages 451 to 477 in the textbook. This is about 27 pages. All right. And also, if you're interested, you can read pages 479 to 493. This is about 15 pages. And these are on subgraph mining. Now, we will not cover subgraph mining in class. And so the second part, 479 to 493 is just for your interest only. So if you're interested, you can read it by yourself. Okay. We'll cover the first part in this chapter. Okay. Oh, by the way, because the second part is on subgraph mining, it's additional for your interest only stuff. It will not be in the exam. Right? So here's an overview of this chapter. So previously in chapter 5, we talked about the a priori algorithm, which is one of the most well-known algorithms in finding association rule. In particular, it helps us how to find the frequent item set and the support counts. There is an alternative algorithm. This is called the FP-Grove algorithm. Now, typically, the FP-Grove algorithm is faster than the a priori algorithm, but it's more complex. So we will give some intuitions and give some examples of how the FP-Grove algorithm works in this chapter. We'll also talk about some interestingness measure of the association rule. That is, what are some of the measures for evaluating how important a rule is? So previously, we mentioned the support requirement and also the confidence requirement in measuring the quality of a rule. However, in addition to support and confidence, there are other measures as well. So we'll take a look at some of these, what we call interestingness measure for association rule evaluation. And then finally, we will take a look or briefly discuss some variants of association rule mining. In chapter 5, the association rule are basically binary association rule. That is, we care about the presence or absence of the items in the rule. There are other models, such as quantitative association rule, or what we call QAR. So for the quantitative association rules of QAR, we do not care only about the presence or absence of items. We also care about the numbers of, or the quantities of the items that is being purchased by the customers as well. So the data would involve some numerical attribute values. And finally, we'll talk about how do we find frequent sequential patterns. So I guess we'll have enough time to go through the FP growth algorithms. Again, the FP growth algorithm is slightly complex. So again, if you have a problem understanding it or following it, let me know. All right, I can repeat. So here is the idea. FP growth is an efficiency method, which is an alternative approach to a priori. The algorithm consists of two components. The first component is to compress a large transactional database into a very compact tree structure. This is called the frequent pattern tree, or the FP tree. So we take the big table of the transactional record, we try to compress it into a tree structure. That's called the FP tree structure. And hopefully, the compressed tree structure is small enough for us to put into main memory for processing. All right. So store the structure in memory to avoid costly database scan. And this is how the FP growth algorithm could improve efficiency. You try to fit things into memory so as to avoid very expensive I/O cost. All right. The second component of the FP growth algorithm is to run an efficient FP tree based frequent pattern mining method. This is a divide and conquer strategy. It's a recursive approach. And the way that how FP growth is faster than a priori is that in the a priori algorithm, as we mentioned, part of the cost, it's the subset testing cost, right? We have to generate a lot of candidate item set and we have to do a lot of subset testing. So as we will see later, with the FP growth or the FP tree structures and FP growth algorithm, there is no candidate generations. There is no subset testing. All right. And so hopefully that will save us some of the CPU cost. All right. So these are the two components or concept, how FP growth could be faster than the a priori algorithm. Right. Now, the FP growth algorithms consist of three phases. Right. The first phase is to clean up the database. All right. Now, you don't have to worry about copying this because we'll explain this a little bit later, shortly. So the first step is to clean up the database. In particular, we will try to remove those items that are not frequent to make the database itself smaller. All right. And then the second phase, or the second step, is to build the FP tree. All right. Hopefully, this is a small enough structure that we can put into main memory. And then the third phase is after the tree is built, we apply a recursive algorithm to find all the frequent patterns or the frequent item sets. All right. So the first two steps are quite easy to understand, but the third one is a lot more elaborate. So, okay, I'll try my best to explain it. Okay, so let's take a look at how this three-step works. Right. I guess the best way for me to explain the FP growth algorithm, the exact algorithm is very, very complicated. But let me use an example to illustrate the main idea of the algorithm. I think that should be sufficient. Right. Now, let's use an example here. In this example, we have just 5 transactions, just for illustration purpose. And let me call these 5 transactions 100, 200, these are transaction ID. And each transactions has include a number of items bought. So each transactions is an item set like these. All right. So the first step of the FP growth algorithm is that let us scan the database one time first. Try to figure out all the frequent one item sets. All right. So this step is very similar to the first step or the first iterations of a priori. Let us find out all the frequent one item sets first. All right. Now, in this example, we have items A, B, C, D, E, F, dot, dot, dot to P, and then we also have the S as well. So altogether, there are 17 items in this example, including A, B, C, D, and so on. Right? There are 17 items. So in this example, let's say the minimum support count that we require for something to be frequent is 3. So we need an item set to be supported by 3 transactions in order to consider it to be frequent. Let's say, for example. All right. So among these 17 items, 6 of them, namely F, C, A, B, M, P, 6 of them, these 6 are frequent. The other are not frequent. For example, the item set S, or the item S, appears only in one transaction, right? So its support count is only 1. So S is not frequent, and we remove it, we discard it. So among the 17 items, only F, C, A, B, and P, the 6 are frequent, all right? And so we compile this little table there. Essentially, that tells us the frequencies or the support count of these 6 frequent item sets. In particular, for the items F, it has a support count of 4, and so on. All right. So first of all, we figure all the frequent item set first, frequent one item set first, and then reprocess the transactions, converting its transactions into a smaller one by discarding those items that are not frequent. So for example, for the first transactions, which include F, A, C, D, G, I, and P, well, F is frequent, so we keep it, right? A and C are also frequent, but D is not frequent. G is not frequent, so these 2 are discarded, right? I is not frequent either, it's not there, so it is discarded as well. So we remove these 3 items from the first transactions, and we sort the items within the transactions according to their frequencies. Okay, so we process the first transactions to obtain this smaller one. Do you understand what I'm saying? All right. So we do this processing on all the transactions, namely discard those items that are not frequent, and then sort the items within the transactions according to the frequency, the support count, the support frequencies of the items. Okay. So after all this processing, this would be the resulting database. You understand? All right. So this first step requires 1 database scan. All right. Okay. So that's phase 1. That's phase 1. All right. Phase 2 is to scan this transformed data set and convert it and construct an FP tree out of it. So here, let me tell you how the FP tree is built. All right. Actually, it's quite simple. So here is the idea. We process each transactions, all right, after the transformation is done. And for each transactions, we construct 1 path in the tree according to the sorted order of the items within the transactions. For example, for the first transactions here, it is F, C, A, and P. So we construct 1 tree path according to the transactions, which looks like that, right? Now, you notice that for each node here, that it is also labeled with an items as well as a count. For the moment, let us ignore these counts for the moment. Right? Just look at the labels of the items, which basically is derived from the transactions. Okay. Now, we consider the now, oops, how come this? Anyway. All right, next, we consider transaction 200. Okay, so previously, after the first transaction is done, we get this, right? We now, next, we proceed to the next transaction, which is FCABM. So we need to construct another path for these transactions. So we get F, C, A, B, M, right? Intuitively. However, you notice that these two paths have some common prefix. So as I said, our idea is to obtain a compressed structure. So how do you do compressions? Well, if there are shared prefix, you merge them, right? So instead of having a completely separate path, when we process the second transactions, this is what we will get. All right, we kind of like merge the common prefix together, right? So do you understand how I construct this tree after I process the first two transactions, right? Now, notice that the counts here, what are the meanings of these counts? Well, the counts that is associated with the node in the tree essentially indicate the numbers of transactions that possess a certain prefix, right? So for example, this A here has a label 2. It means that if you go from the root to this node, you see FCA. So this 2 here means that there are two transactions whose prefix are FCA. All right. Now you notice that this is 1. Well, this node here represents the prefix FCAB. And this count is 1. It means that for the first two transactions, there is one transaction whose prefix is FCAB. All right, is that clear? Okay. So you process all of these transactions, adding the paths into the tree, merging prefix if necessary, right? So here we process the third transactions, which is FB, and this is the resulting tree, right? F is a common prefix. So now this node would have a count of 3 because there are 3 transactions with the prefix F, all right? And FB is given by this path, and there is 1 transactions with the prefix FB, all right, and so on, okay? So after you process all of the transactions in the data set, eventually you get this tree, all right? Okay, so intuitively, you understand how this tree is built, right? Now, nooks with the same item label. So after this tree is built, we have to do one additional step, which is that let's take a look of all the nooks that have the same item label. We want to form a linked list or change among them, all right? Which is illustrated by this, okay? For example, we have C here. Now, let's say we have B. This node is labeled B, this node is labeled B, this node is also labeled B, right? So we want to form a change that connect them together. And this is the chain from here to here to here. So we link them up, all right? And at the same time, we also create what we call a header table. Essentially, this header table is simply telling us where do we find the change of each item. So for B, this header table with a pointer that points to the head of the linked list, which if I trace the pointer, we'll be able to retrieve all the nodes in the tree that is labeled B, right? Likewise for the others, all right? And in the header table, I also maintain the frequency counts of the various items, all right? So far, do you understand how this tree is built? Okay, we process the transactions to obtain paths, merge the prefix of the path if necessary. After the tree is built, we link up all the nodes in the tree that have the same item label, and the heads of those linked lists is given by this header table. All right, so this is what we call the FB tree. All right, okay, any question? No? So this is phase 2, building the FB tree. Now, phase 3 is more complicated, which is given this FP tree that has already been constructed, we assume that it fits into main memory. And the next phase is to extract the frequent item sets or the frequent patterns from this tree. All right. So here, let me read out the steps. I do not expect you to understand all of these, but don't worry, we'll go through an example to illustrate. All right. So the general idea of the first phase, which is to find the frequent item set or extract the frequent item set from the FP tree, is a divide and conquer approach. It recursively grows frequent patterns path using the FP tree. And here's a discussion of the method. For each item, we construct its conditional pattern base and then its conditional FP tree. And then we repeat the process on each newly created conditional FP tree until the resulting FP tree is empty or that it contains only one path, and that is considered the base case of the recursions. And from the single path, each possible item subset would give us a frequent pattern. Again, I do not expect you to understand this fully, so we'll use some example to illustrate, all right? But first of all, let me just explain a little bit about what we mean by divide and conquer, all right? So in this example here, we have 6 items, namely F, C, A, B, and P, okay? So by divide and conquer, what we wanted to do is to find out all the patterns, all the frequent item sets that ends with a P, all right? This is the first task, all right? Another task is to find out all the frequent patterns that ends with an M, right? So our task is to find out all the frequent patterns, but let us divide it into smaller tasks. One smaller task is to find all the frequent patterns that end with a P. Another smaller task is to find all the frequent patterns that end with an M. Another task would be to find out all the frequent patterns that end with a B, and so on. All the patterns that end with an A, all the patterns that end with a C, all the frequent patterns or items that end with an F. All right, so we have 6 items. So let's divide the whole task into 6 subtasks. Each one, it has a specific item being the last one in the pattern. Do you understand what I'm saying? All right. So now the question is, how do we find all the frequent patterns that will end with a P? Okay. So the basic idea is to do recursion. All right. We extract certain part of the data from the database that are guaranteed to have P at the end. And then based on this data, we build a conditional FP tree. But this conditional FP tree are guaranteed to have P at the end. All right. And based on this FP tree, we find all the possible frequent patterns among them. And if we add P at the end, that will give us all the frequent patterns that end with a P. All right, and so on. Okay. Again, it is hard to imagine, by these details, but again, we will show an example shortly. All right. So we start with the last item in order, that is P. We follow the node pointers starting from the header table and traverse only the paths containing P. And we accumulate all transform prefix paths of that item to form a conditional pattern base. And then we recursively solve the mining problem for the conditional pattern base and concatenate each frequent items found in the conditional pattern base with P. So let us use an example to illustrate. All right. So previously, I said that, well, we are dividing the problem into 6 subproblems. Why 6 subproblems? Because we have 6 items, right? F, C, A, and P. And we want to do it solve each one at a time. So we start with the least popular item, let's say P. So now our objective is to figure out all the frequent patterns that end with a P. So when we say conditional FP tree, the condition is that all of these patterns ends with a P. All right. So how do we do it? Well, we have this FP tree built. Now our objective is to construct or find out the patterns that end with a P, right? So naturally, what do? Is that we need to extract the information from this FP tree, the part that concerns P, all right, or the parts that actually ends with a P. So what do? Well, we go into the header table, find the pointer for the P entry to locate all the nodes in the tree that has P in it. All right. So we follow this link, we find this P, right? So we retrieve this part of the tree. Follow this next pointer, we get this P, and we extract this path of the tree. All right. So from the header table, we locate all the nodes that mentions P, and then retrieve their paths. All right. And that is, in this case, we have this as a result. Right? So this tree is just an extraction, a part of the FP tree that we built that concern P. You understand what I'm saying? All right. Now, notice that we have some counts in the nodes. For example, this F4. What is that for? That for means the numbers of transactions in the database, in the whole database, that have F being the prefix of in the transactions, right? However, this for includes things of the whole tree, right? So we have this for here because we have two prefix called FCAMP. We have one prefix called FB. We have one prefix called FCABF. And that's why we have 4 here, right? But in our subtask, which is the one that we only concern P, we should not care about this path. We should not care about this path either, right? So that means that this count 4 is not quite right if I'm only concerning the patterns that end with a P, right? So after this path have been extracted, we have to do some fixing, of the, of the information there. So in particular, what do we need to do is that we have to fix the counts, all right? In particular, so how do we fix the counts? Well, we start at the bottoms of the paths. We have a P2 here with a P1 there. We propagate this count upwards to the tree. So here is a 2. So we propagate, this is a 2. We propagate, well, this 3 is actually not correct. So we have to fix it to make it a 2. You understand what I'm saying? We go up. Well, this is a 3. Well, it's not correct because there's only a 2 along this path. And so this would also be updated to 2 as well, right? So we do the same thing for the other path. This is a 1. Well, we propagate this count upward. Well, in this case, there's no need to fix anything, right? So we have to fix this count, okay? But let us do the illustrations of this slightly later, all right? Now, based on this part of the tree, after we have fixed the counts, okay, essentially, what we are saying is that what is the information that's being carried about by this tree is that we have this conditional pattern base for P. All right, what does it mean? So from this, we see what? We see if I ignore the P nodes, because everything ends with a P. So practically we can ignore it because every path would end in a P, right? So we look at this part of the tree, we see FCAM. And these counts are 2. What does it mean? It means that there are 2 FCAM here, right? Along this path, we see a C and a B with a count of 1. That means we have 1 count of a CP pattern, okay? All right? So from this tree, we can derive this data set, all right? So essentially, that is the data sets that we can derive from the original bigger data sets if we only consider P as a conditional pattern, all right? So now the question is, if this were the database that we have, what would be the FP tree of this data set? So let us ignore the bigger data set, origin data set for a moment. If this were the data set that we have, and if we are asked to build an FP tree out of it, what would be it, how it would look like? All right. So let's try to build this. Okay, the first transaction is FCAM. So we have F. Actually, I should do it this way. If you can still remember, to build the FP tree, we go through the 3-step, right? The first step is to remove the non-frequent items. Okay, so remember in this example, we require a minimum support count of 3 in order to consider something to be frequent. So if you look at this data set, what are the frequent items? Well, F occurred 2 times, right? So it's not frequent. C occurs 3 times, so this is frequent. A occurs 2 times, so it's not frequent, and so on. So the first step requires us to throw away all those infrequent items, right? And this data set will be transformed to just C, C, and C, right? And so what would be the FP tree that you will build out of it? Well, you process the first transactions, you build the tree with this label. You process the second transactions. Well, this is the same path, so you increment this count. The third transactions, the same path, so you increment this count. So eventually the tree that you get is just this, right? And now there's only one path in the database. And so that's the base case. And the possible patterns that you can obtain from it would be all the possible subsets of the items here, which include the empty sets and C. All right, but do not forget this is conditional on P. That is to say, whatever patterns that we can derive, we have to append P at the end. All right, so this derive the frequent patterns or the frequent item set P. This derive the pattern CP. All right, so these are the 2 patterns that we can obtain, right, if this were the data sets that we have. All right, so that's, I show you what's the logic, but how exactly do we perform this kind of logical deductions with the tree? This is what I'm going to show you up next. All right, okay, one more time, let us reset a little bit. So first, I would like to consider the item set P, all right, the item P. So I consider the original FP tree that I built. Okay, I'm interested only in those patterns that end with a P. So I look at the header table, find the entries of P, extract the link. So this is the nodes that concern P. That's the nodes that concern P. I extract their paths. That creates this tree. All right. And then I said the next step is that we need to update the counts. So after the counts is updated, we get this tree, right? So after this is updated, then the next step is to remove the load count nodes. So again, one more time, we have a minimum support requirements of 3. So we look at these paths and see what are the nodes that do not provide enough support. What are the items that do not provide enough support? Well, in this tree, we have only one node with F. The count is 2, which is less than 3. So this node should be removed. All right. And for example, C, there are 2 nodes that contain C. All right. And the total count is 3, which is enough. So C should be retained. For the other one, let's say A or B or M, these counts are not sufficient. So they should all be removed. So after the removal of the low count nodes, this would be the results. And then here we can merge them together because this is the same path. And this is what we get. So this would be the FP tree that I previously showed, right? But this tree could also be obtained procedurally by the steps. All right. So after this is obtained, we say that this is the base case because there's only one path in the tree. And all we need to do is to enumerate all possible subsets of this, which include the empty set and also C, right? the resulting conditional FP trees of P is this. And if we extract all transactions involve P and build that frequent patterns tree, this is what we would get, right, as I explained. So the frequent patterns that we could deduce would be P and CP. This is all the possible subset that we could derive from this. And for each one, we append P to the end, and these are the possible patterns. Right? These are the patterns that end with P. All right. So let us do one more example. Okay. So that we have completed this subtask to obtain all the frequent patterns that add with a P. What about the next one? The next one is to find out all the frequent patterns that end with an M, right? So we follow the same procedure. We start with the original FP tree, but this time we want to do the conditions on M. So we go to the header table, find the entries of M, and retrieve the linked list, right? So these are the two nukes that we found to be concern M, and we retrieve the paths out of it. So that's the part of the FP tree that concern M, and it looks like this, right? Okay. Now, if you can still remember the procedure, is that we need to do some count fixing. Okay? So we propagate 2 and 1 upwards. All right. So this is a 1. So we check this. Oh, this is 1. This is okay. And then we propagate it upward. Now this one has 2 child. One is a 2. One is a 1. So the total count should be 3. So this is good, right? Propagate upward is 3. Propagate upward. This should be 3, but this is 4. So we have to fix this counts. Okay. So this is about count fixing. You understand what I'm saying? All right. So we update the counts, and we will get. So if we update the count, this is what we will get. All right. So after the count is updated, then the next step is to remove the low counts nodes. Okay. What are the nodes that have low counts? Well, B is low counts, so we remove it. That's the only one that we can remove. All right. And so the resulting FP tree looks something like this. Or the conditional FP tree looks something like this. Now this has only one path. So that's the base case. And if you see only one path here, the next step is to enumerate all possible subset of it. So what are the all possible subsets of this stuff? Would be empty set, F, C, A, F, C, F, A, C, A, and also F, C, A. These are the all possible subsets that concern the items F, C, and A, right? But this is conditional on M. So whatever patterns that we extract, we should put M appended at the end. And so this would derive these patterns. Okay, so these are all the frequent item sets, or sometimes people like to call the frequent patterns that have M at the end. You understand what I'm saying? All right, so this is just another example. Now, if you're interested, I really suggest that you go home and try to figure out how to solve the other 4 cases and see whether you will be able to follow this procedure and obtain all the frequent patterns for all these 4 subtasks. And these are some of the hints of all the 6 cases. All right, let's see whether you will be able to build the conditional FP tree accordingly. Right, for example, for M, the conditional FP tree is this. What it means is that we have this. There's just one path, F, C, and A, and with the corresponding counts being 3, right? And this is the this representation. All right. As another example, and this is the conditional pattern base. It essentially tells like what is the data sets that we extracted that help us build the FP tree. Okay, so let's see whether you'll be able to build this conditional FP tree following the procedure, and you can check the result according to this columns of the table. All right. Okay, so here let me very briefly explain, mention some of the advantages of the FP growth algorithm. The advantages here is that there are no candidate generations and no subset testing. Sorry for the typo. Okay. So you notice that for the whole procedure, we never generate any candidate sets, right? We never do any subset testing. Okay, so no subset testing, no candidate generation. So hopefully that would make the computation more efficient. It uses a very compact data structure called the FP tree, right? Essentially, the FP tree can be considered as a compression of your whole data set. Excuse me. And it eliminates repeated database scans. So remember, in the FP growth algorithm, you have to build you have to do a couple of steps. The first step is you just have to scan the database one time to convert each transaction into a smaller transaction, right? Removing all those non-frequent items. And then you have to scan it the second time to build a tree. So there's only two passes over the data set. And the basic operations is counting and FP tree building. Usually it's much more efficient than the a priori algorithm, especially for those scenario where there are many long patterns and common patterns, all right? But the disadvantage of the FP growth algorithm was that it required quite a bit of memory because you are creating an FP tree and you're fitting the FP tree into main memory for processing. So if the FP tree is quite large, essentially because the FP trees can be considered as a compressed versions of the database. So if your original database is huge, then even though you can compress it into an FP tree, the FP tree could still be very large, and it may not fit into memory so well. But nowadays, memory is very cheap, so it's the FP growth algorithm is even more practical nowadays. All right. Okay, so that's about it for our discussion today on the FP tree, the FP growth algorithm, and also some analysis of the association rule mining. And let us take another 5-minute break, and when we come back, we'll have a, sorry. Yes. Oh, okay, okay. The question is, so far in our discussions, we talk about how the FP trees are built and how these frequent patterns are obtained, right? And the question is how, then what is the next step? You know, how do we generate association rule? Basically, the FP growth algorithms serve the purpose of completing the first step of association rule mining. Now, if you can remember, to derive the rules from the database, the first step is to find out all the frequent item sets. And then, based on that, we can derive the rules, right? So the FP growth algorithm essentially is for the purpose of the first step, to try to find all the frequent item sets. So these frequent patterns that I mentioned here, these are the frequent item sets. So FCAM is a frequent item set. If I could write it better, it would be like this. FCAM, you know, this is the frequent item set that we compute, right? Versus things like, oops, sorry, I don't have that slide here, but then if you can remember, we want to build the frequent item set table, and those, you know, we want to determine which items that are frequent. So basically, these are the frequent item sets. Even though I didn't write them like they are item set, but for example, FCAM, when I write FCAM here, it actually means this item set. Yes, then after you get to know that this is a frequent item set that is derived from the FP growth algorithm, then in order to generate rules, you have to partition this one into a left-hand side and a right-hand side, and then check the confidence requirement. Right, thank you for the questions. Any other questions? All right. If not, then let's take a 5-minute break, and when we come back, we have a tutorial on recommender system. Right? Good.
Okay. And in this tutorial, we'll talk about recommender systems. And actually, recommender system is everywhere when you're visiting the internet, like on shopping websites, you will see products recommendation. So they will recommend you some products that you're likely to buy. And on social media, you'll see some posts recommendations or some friend recommendations that the system thinks that you might be interested to follow. And then on streaming services, they will provide you some recommendations on movies or TV series. So why do we need this kind of recommender systems? So like for users, for you, when you are using the internet, you can get some personalized recommendations, some personalized content, and you will not be overloaded with the information provided by the service provider. And then for the service provider, they can offer better service and which let them make more profits. So this is why recommender system will be so common, especially in commercial websites. And how do we make recommendations? So recommender systems are kind of like the KDD process we've discussed. So from data, we apply some recommendation algorithms to find some useful patterns. And then we evaluate these kind of patterns to see if let's say the recommended items were visited by the user or not. So we have the personalized content recommendation, and then this recommendation will be evaluated, and then they can adjust their recommendation strategy. So what kind of data we can collect from what kind of data we can collect so that the recommender system can use it to make recommendation? So let's say on streaming services, for users, we can collect the ratings given by the users or the view history given by the history that the user access the content. Or we can also provide some survey for the user to see what kind of content that the user may like. So this kind of information can be used as a data to provide recommendation to the user. And then for items, we can collect some information such as the category of the movie or the content description of the movie so that it is easier to compare which movie is similar to another movie. So these are some kind of information that we can collect. And of course, you can think of more data. So the more data you have, probably the better the recommendation would be. So here is just an example that we'll go through in this tutorial. So let's say we have 4 TV series here: Breaking Bad, Friends, The Big Bang Theory, and Modern Family. And there are 5 users, including you as the 5th user. So you have seen the first 3 TV series, and then you have also given some ratings. Let's say the ratings ranges from 1 to 5. And then some other users 1 to 4, they also watch some of the series, and they have also given some ratings to the TV series. But also there are some series that the user haven't watched. So based on your ratings and the ratings given by others, how will recommendation systems make recommendation to you? And the technique we are going to introduce in this tutorial is collaborative filtering. So the term collaborative means that the users, the information from other users are used collaboratively to predict the rating of yours or to predict the missing ratings. And then there are 2 broad categories of collaborative filtering. The first one is called memory-based. So the ratings are loaded to memory and then do some computations. So this is why it is called memory-based. Another term of this memory-based collaborative filtering is the neighborhood-based collaborative filtering. So the neighborhood-based means it's kind of like the nearest neighbor method. So they find some of the similar items or similar users and then use their ratings to predict the rating. So we have user-based collaborative filtering. That is, the ratings provided by users that are similar to you will be used to make predictions. So they first identify some of the similar users. They have the same, you and those users have the same taste. And then they use their ratings to make predictions. And on the other hand, there's another type called the item-based collaborative filtering. So they first identify some of the items that are similar to the items to predict, and then use them to make predictions. So let's say for user-based collaborative filtering, they will first identify the user that is most similar to you, and then use it to make prediction. But then for item-based, they will find which TV series is more similar to the one to be predicted, and then use its rating to make the prediction. And we will give the details later. And then we can also use some other techniques that we have introduced in this course to do prediction. And these kind of techniques are called model-based collaborative filtering. So we can use naive-based classification to classify whether you like the ratings, you like the movie or not. Or we can use decision trees or association rules. And we can also use latent factor models. We don't cover this in this course, but the rough idea is that they use some matrix factorization to recover the missing values in this big matrix. But we will not go into the details for these latent factor models. So for user-based collaborative filtering, you first identify similar users that are similar to your watching history, and then they use it to predict ratings. And there are some issues for this computation. So for example, users may have different scales of the ratings. So sometimes you are very harsh on predicting the movie ratings. So you might give a low score, like only 1 to 3 on most of the movies. Whereas some users may be a bit nicer, like you only give 3 to 5 as the ratings. So if a movie is not so good, you give it a neutral rating. And if the movie is really good, you give it a 4 marks. So this kind of scaling difference can be taken into account when we are doing user-based collaborative filtering. And then different users may have rated different items. So there will be some missing inputs, and we will see how to handle these kind of missing inputs. So some notations. Let's say we view this user item table as a matrix. So we denote each item Rij, where this I is the user and J is the item. So we have R12, user 1, item 2. R12 will be 3. And R21 will be null because the user hasn't rated this item. The user hasn't watched the movie. And what we're going to do is we are trying to predict R54. So user 5's rating on item 4. And as we are using user-based collaborative filtering, we will try to identify some similar users among user 1 to 4 and use their ratings on item 4 to predict this rating. And we see that for user 1, he or she hasn't rated item 4. So we will not include user 1 when we are doing the prediction. So we will just we're just using user 2, 3, and 4, using their ratings to predict whether you will like this movie or not. And as I mentioned that in the challenges, one of the challenges is that the users have a different scale on the ratings. So one of the adjustments that we will make is that we will compute the mean center ratings. So essentially, we are trying to center the score such that the mean of the score given by a user would be 0. So we center the mean to 0, and this is why it is called mean center ratings. So the computation is simple. What we will need to do is that for each user, we compute the mean of the ratings given by the user. So for user 1, the ratings will be 4, 3, and 3, and the mean of these 3 will be 3.33. And then we subtract each rating by the mean. So 4 minus 3.33 will be 0.67, and this will be the mean center ratings given by user 1 to item 1. And we will denote it with Rij bar. Okay. So after doing all the computations, we will get the matrix that shows the mean center ratings of all the users and all the items. And then we will make predictions based on these metrics. So this step is to alleviate the effect that the user has a different scale on the ratings. So now we can do the prediction. So actually the prediction is quite simple. The idea is to use the weighted ratings, and the weights are computed by the cosine similarity between the users. So we are going to predict user 5, user 5's rating on item 4. So for each user, we compute their cosine similarity based on their ratings. Since user 1 didn't rate item 4, so we exclude this one. And then for user 2, we see that user 2 rated item 2, 3, and 4, and user 5 rated item 1, 2, and 3. So actually only item 2 and 3 are both rated by user 2 and user 5. So we will use these two numbers to compute their similarity. So the similarity between user 2 and user 5 would be the cosine similarity between these two values. That would be the ratings are item 2 and item 3. And similarly, this is item 2 and this is item 3. And computing cosine similarity, I think we have mentioned it in early part of the lecture. So this would be the formula. And then we see that the similarity is a negative value, which shows that user 2 and user 3 may be quite opposite in their opinions. And then we repeat the same process for the other users. So for user 3 and user 5, we see that they both rated items 1, 2, and 3. So in this case, we will have more data to do the similarity computation. So the similarity between these two users, again, we are using the cosine similarity. And also we do it for user 4 and user 5. So after this computation, we have the similarity between the user 5 and all the other users. Then we do a weighted average. So we take the scores given to item 4 and the similarity to user 5, and use these two to compute the weighted average. So we multiply 0.33 by negative 0.89. And then we multiply these two. And also we multiply these two. 0.71 multiplied by negative 1. And then in the denominator, we sum up the weights, the absolute value of the weights. So note that all of these should be positive when we are computing weighted average. And we got a value of negative 0.37. So this value would be the value, the predicted value for the mean center ratings for user 5 on item 4. And if we want to get the original rating, that is, if we want to recover the ratings here, we will need to add back the mean, because what we have just computed is the predicted mean center ratings. So here, we will need to add negative 0.37 with to the mean 4, and we will get 3.63. This would be the predicted rating for user 5 on item 4. So this would be the part of user-based collaborative filtering. And just some discussion here. So we are using adjusted cosine similarity to, we are using mean center ratings to compute the cosine similarity instead of the raw ratings. And is it possible that we use the unadjusted cosine similarity? That is, we don't use the mean center ratings, we just use the raw scores and then do the computation. Well, it is possible to do so, but it is not an ideal way because it doesn't take into account of the different scales of the user. But since this kind of recommender systems is also a knowledge discovery process, you can compare the two and see whether there's a big difference, and you will need to interpret the results by yourselves. And in this example, we compute the similarity of the users based on the items that were rated by both users. So is it possible that we fill in zeros as for the missing inputs? And yes, it is also an approach, but the assumption would be that the user gives an average rating on the item that the user hasn't rated. Whereas in the previous approach we discussed, we just drop these items and we ignore it in the computation of the similarity. And there is a little bit of effect on this, but most of the time the effect will not be too significant. And is there any other similarity measure that you can use? So as long as you have a similarity measure, then it will be fine. And one of the possible approach would be using the correlation coefficients. And the correlation coefficient would be different from the cosine similarity if we are using, if two users do not rate the same amount of items. But if the two users rated the same items, then the correlation coefficient would be adjusted by the mean. And this is equivalent to the mean center ratings. So you can try to see whether there is a big difference between the correlation coefficient and cosine similarity. And then we'll also go through an example on the same example using item-based collaborative filtering. And there are still the same issues when we're using item-based collaborative filtering. So we will have missing inputs, and different users will have different scales on the ratings. And when we are computing mean center metrics, note that the process is the same as what we saw earlier in user-based collaborative filtering. So we will subtract the scores by the mean of each user's ratings, not the mean of the item's ratings, even though we are using item-based collaborative filtering. But the process of computing this mean center rating, mean center matrix is that we want to remove the effects of the users having different scales. So we are actually subtracting the mean of the user's ratings, not the item's rating. So if we are going to predict the score given by user 5 on item 4, we will need to identify some similar items and then use the score given by user 5 to predict this item. So the process is similar. We compute the mean center ratings. So this mean center rating matrix is the same as the one we saw earlier. And then we do the cosine similarity to find out the similarity between item 1 and item 4. And similarly, we do it for item 2 and item 3. So we have the similarity scores between each item and item 4. So we see that item 3 has the highest similarity with item 4 according to user 5. Well, according to all the other users. So we will use user 5's ratings on item 3 mostly to predict the score on item 4. And we see that item 1 is similar to item 4. So we will also use it, but in a negative manner. So it will be multiplied by a negative value. So again, we are computing the weighted average of the scores given by user 5, weighted by the similarity between each item and item 4. So we will have -1 multiplied by -0.69 and -0.2 multiplied by 1 and 0.79 multiplied by 0. And then the denominator are the absolute value of the weights. And we also get the value 0.29. And then remember to add back the mean of user 5. So the rating here we see is 4.29. And this is much higher than the user-based prediction. And the reason is that in item-based collaborative filtering, the items that are more similar to item 4 has the highest effect. Whereas in the user-based collaborative filtering, it is the user that have the most similar taste to you have the highest effect. So these are affected by different factors. And the effect is quite obvious here because we have very few user and items. And then we will show how you can use Python to implement the recommendation systems. But because the implementation does not require some specific packages, so I will not go through the details of the code, just to show you what we have and what would be the task that we are doing in this coding. So in this movie lens data set, there are two files, movies and ratings. So what we will need to do is to, based on the ratings, predict the score given by a user with UID equals 1 to the movie 2 using user-based collaborative filtering. And we can see that in the movies table, it gives some details like the title and the genres of each movie. And actually, we are not working on this table, but this table, I put it here just to let you know what each movie is about, so you can have a more understanding on the data. What we will be focusing on is this rating table. So in this rating table, it gives the user ID and the movie ID. So user 1 gives a rating 4 on movie 1. And there's a timestamp which we can ignore. And just to let you know that these ratings ranges from 0.5 to 5, as we can observe from the data. So remember that in user-based collaborative filtering, what we did is that first we compute the mean of the users. So computing mean, well, it's quite simple. You can just sum them up and divide it by the numbers. Or when we are using pandas, when we're using data frame, there's a function called mean, which you can use. So the first step, computing the mean center ratings, we'll be using this mean function. And then computing cosine similarity, we will be using the cosine similarity matrix in the scikit-learn package. So remember that scikit-learn is a very common package for machine learning. So we will use this cosine similarity to compute the weights. But we write the function here because we need to do some processing steps to remove the items that are not rated by the user. So we will need to filter out some of the items. And because each line here is a bit long, so in the next few slides, I've shown you step by step on what each element is, so you can refer to it at home when you're practicing this Python coding. And finally, what we'll need to do is to compute the weighted score. So computing the weighted score, basically you get the score of each user, and then previously you would have computed the similarity score between each user and the item, and then you just multiply them, and then divide it by the weights. So to efficiently multiply the weights and the scores, it is similar to getting the vector and then use a dot product. This will basically do a pairwise multiplication and then do a summation. And each part of the code is also explained step by step here. So you can take it as an exercise. And finally, just to let you know that we also include some of the discussion on model-based collaborative filtering. So you can use association rules or naive-based classification. And this will be left to you for self-reading. And yeah, if you have questions regarding the slides, after you have read this, you can feel free to email me or schedule a consultation hour with me. And thank you.